Mapua Phil-Lidar 1 project is part of a nationwide project under the Phil-Lidar 1 program, funded by the Department of Science and Technology, or DOST, through the Philippine Council for Industry, Energy, and Emerging Technology Research and Development, or PSERD. The program is tasked to do the hazard mapping of the Philippines using LiDAR technology. Mapua does the LiDAR data processing and flood hazard modeling and mapping of 26 river basins, 6 in Batangas Province, 5 in Cavite Province, 13 in Quezon Province, 1 in Camarines Norte, and 1 in Camarines Sur. The models that are produced could be used to predict flood levels and flood inundation in floodplains. Information are precise because LiDAR digital elevation models are 20 centimeter accurate in the vertical, or elevation, and 50 centimeter accurate in the horizontal, or in the geographic location. In this project, we created different maps at different rainfall return periods so that when weather agencies say that a certain storm or typhoon will pour this much of rain with this equivalent rainfall return period, we could immediately locate exactly in the map which will be flooded to plan an evacuation and determine where to safely shelter our families and constituents. The Mapua Phil-Lidar 1 project is divided into 3 components: the terrain modeling component, the flood modeling component, and the field acquisition and validation component.
Before I discuss the different tasks of the terrain modeling component, let me first give you an overview on the type of data we are processing. Digital elevation models, or DEMs, are models that simply visualizes the terrain conditions on the surface of the Earth in 3 dimensions. It has 2 kinds. The first one is the digital surface model, or the DSM. Simply the elevation values from top of buildings, tree canopy, power lines, and other type of man-made and natural features. On the other hand, if we remove those land covers, we expose a smooth, bare earth elevation model, which is called the digital terrain model, or the DTM. As a member of the terrain modeling component, we have 3 main tasks to do. First, to manually edit the digital terrain models. In manual editing, we remove the bridges that can impede the flow of stream, and we fill the pits so that the water will not be entrapped in this area, and thus, we correct the flow of the river. Second, to burn the bathymetric data in the digital terrain models. In bathymetric data burning, we integrate the field bathymetric data within the extent of the river. After integration, we interpolate those points to create the surface of the river with the correct elevations, which will be then used by the flood modelers. Third is to extract the features in the DEMs, or the digital elevation models. In feature extraction, we digitize the water bodies in DTM, the bridges, roads, and buildings in DSM, after which we attribute those features. To summarize everything, the 3 primary tasks of a terrain modeler are to manually edit the DTMs, to burn the bathymetric data in the DTMs, and to extract the features in the DEMs.
One of the important components of Mapua Phil-Lidar 1 project is the field acquisition and validation component. We are responsible for data gathering. We conducted numerous fieldwork and survey, such as reconnaissance survey, attribution survey, flood and extent survey, and river flow measurement for normal and extreme condition. I can say that this is very challenging and fulfilling task. Indeed, this project would be a great help to reduce flood hazard and have a great impact, especially to the local communities.
The first task of field personnel is to conduct courtesy call and reconnaissance on the municipalities or cities covered by the river basins, to inform them about what the project is all about, and also to ask assistance in conducting the fieldwork. For feature attribution, the field personnel will determine the coordinates and the names of the establishments, roads, and water bodies by taking geotag photos using the handheld GPS. This task is fun, but also the most challenging part, because some areas are far from the city and also mountainous. Some have no means of transportation, so the field personnel have no choice but to walk. The good side here is that we get to see how beautiful our country is, and we get a lot of exercise by trekking. Some areas are dangerous because there are frequent encounters between soldiers and militant groups. Some field personnel heard gunshots while gathering data, so some barangay officials asked them to stop and just go back if the fight is over. In flood map validation, the field personnel will locate validation points for validating the flood hazard map using handheld GPS by interviewing some residents with knowledge or had experienced flooding in their area. One of the major tasks of the field personnel is to conduct river velocity measurement of the river with or without the influence of precipitation. There are three parts in conducting the river velocity measurement. First, base flow. In this scenario, the field personnel are tasked to record the normal stream velocity of the river for 3 hours in the morning and 3 hours in the afternoon. On the other hand, event flow, the field personnel are also tasked to record the stream velocity for 6 hours or until the water level and stream flow becomes normal during rainfall event. While doing both methods, the field personnel also monitors the water level of the river to be able to compute for the discharge of the river and produce a hydrograph. The challenging part here is some rivers do not have existing bridge for the field personnel to deploy their equipment for measuring the river velocity and depth. So to measure the stream velocity, they installed a cable wire across the river and tied their rented boat at the center to measure the flow. The field personnel also installed few rain gauges in some rural areas that still do not have existing automated rain gauges. Obtaining rain gauge data during rainfall event is important for the flood modeling component in calibrating the resulting hydrograph of the river.
Generally, the flood modeling component is responsible for all the hydrologic process needed to generate flood hazard maps. This includes the generation and calibration of the hydrologic and flood models of the 26 river basins and the validation of the flood hazard maps. After the field acquisition and validation component gather data from the field, we process those data to plot the discharge versus time graph of the observed data and to generate a rating curve, which are then later used in calibration. To calibrate a model, a setup of HMS model is first done, and then we simulate the complete hydrologic process of the watershed systems using hydrologic modeling system, or also known as HMS. The software includes many traditional hydrologic analysis procedures to produce model outflow. We simulate the model in different return periods: 5-year, 10-year, 25-year, 50-year, and 100-year rainfall event. These return periods are based on the precipitation data from Philippine Atmospheric, Geophysical, and Astronomical Services Administration, or PAGASA. Another process being done by the flood modeling component is the generation of 1D flood maps using river analysis system, or also known as RAS. This allows us to produce one-dimensional flood maps. The model produced a simulated water level at every cross-section for every time step for every flood simulation created. The 1D flood maps help us to determine the extent to which the water will flow during storm or heavy rainfall event. Or simply, it helps us to identify the flooded areas within the model. In the RAS models, we use the burned bathymetric data processed by the terrain modeling component. And lastly, the generated 2D flood models help us to determine the flood inundation extent of the river and its corresponding water depth. These are validated by comparing the depth in the model and the flood validation points from the field data. The accuracy of the flood model is measured against the observed values by computing the root mean square error between the data.
The Mapua Phil-Lidar 1 project is a big break, not just for our School of Civil, Environmental, and Geological Engineering, but the entire Mapua community. It is the first time in the history of the institution that we were given a huge amount of fund for a 3-year project that involves about 14 higher educational institutions across the country. The project is very challenging for me as an administrator because it doesn't only involve the technical aspect but also how to lead these talented people, a lot of talented people, towards a common goal. Flooding is a perennial problem in many communities in our country, and it's the objective of this project for us to be able to generate more accurate, more reliable flood maps or models that can aid or be useful in any disaster preparedness, mitigation, adaptation program of our local government units. Because in the event of any disaster, every second counts. In behalf of the Mapua community, I would like to thank the DOST and PSHERD for giving this opportunity for us to be on board in a very important national project.
The project is a hallmark of our government's effort to mitigate our perennial problem of flooding in the country. And this must be steadfastly practiced to protect our resources and to save more lives.
When it rains,
When it rains,
When it rains, it pours.
The Mapua Phil-Lidar
One team is all yours.
Mapua Phil-Lidar 1 team is all yours.